Hello everyone, and welcome to another live session for the online class. I hope everyone had a good holiday, and many of you, of course, not from the US are unfamiliar with this gorging eating holiday that Americans have specialized in. It even exceeds Christmas in my estimation. But anyway, the floor is open for astronomy today. I'll take your questions.
All right, the first question is from someone who is on with us live, who asks, what do you think about the origin of the universe before the Big Bang? Where did space come from?
So it's a good question, because the Big Bang model just describes the evolution of the universe from a very hot, dense early state 13.8 billion years ago. The Big Bang model itself does not say anything about what caused the Big Bang or the precursor state, if there was one. And in fact, time begins with the Big Bang, so the Big Bang does not even describe a meaning to either space or time before that event. So the simple answer to the question is you're in the realm of speculation. So there's no theory akin to the Big Bang that talks about the earlier state. But since the Big Bang started as a quantum event, because at one point the universe was smaller than an atom, just extrapolating backwards to essentially infinite density and temperature, the speculation goes that there may have been other quantum events, other universes. That leads to the multiverse idea. And so there's a rich realm of theoretical speculation based on precursor to the Big Bang involving quantum fluctuations. But there's no underlying theory that lets us do serious calculations about that situation. In fact, we need a quantum theory of gravity, which we currently don't have. So I think the conservative and cautious thing to say is we have no idea what happened before the Big Bang, or even if there was a before.
Right, the next question is again from someone who is on with us live. I'm starting to look at the night sky with a pair of celestron 20 by 80 binoculars. I was wondering what would be some of the best things I could see with these binoculars.
So for binoculars, the real distinction between binoculars and small telescopes is the field of view. The best binoculars are actually really good. Optical quality of binoculars has improved enormously in the last 20 or so years, especially with sort of high quality but light plastic components. So, but the binoculars of the past used to weigh a lot, and they're really hard to hold upright. You can also, of course, have a tripod or viewing stand so that you don't have to carry them. So in general, binoculars are better for wider fields, because telescopes, even with a wide-angle eyepiece, tend to be looking at smaller fields. So the typical good objects to look at with binoculars would be star clusters. If you want to look at something that's in the evening sky in the northern hemisphere right now, the Pleiades is a great place to start. It's really obvious in the northern sky. It's called the Seven Sisters because of the 7 young stars that are visible to the naked eye. But with a good pair of binoculars, you can see actually several dozen stars and even the gauze of gas that this young star cluster formed out of. So basically, star clusters, young star clusters, or even globular clusters are the best kind of objects to look at with binoculars. You could also look at M31 Andromeda, or M101 or M33, 3 galaxies in the northern sky, northern evening sky currently. Those are still slightly better with a telescope than with binoculars, but they're certainly visible. Andromeda, of course, is visible to the naked eye if you're at a dark enough location. So generally, these are the best things to look at. Planets, not so much, although you can see the moons of Jupiter through binoculars. It's still better done with a telescope. Binoculars are, of course, the best way to get acquainted with constellations and learn how to hop around the sky and navigate the sky. So for orientation, they're extremely good. It's easy to get lost with a telescope, either not knowing how to point it, unless if you don't have one of those automated telescopes, or being pointed at such a narrow piece of sky that you lose the big picture of where you're located.
All right, the next question is from Stephanie, who is on with us live. She asks, if nebulas are where stars are born, wouldn't we be seeing nebulas all over the place? Why aren't there more nebulas known to us? Are they just too far away?
They are. There are a number of nebulae that are available, and to answer the last question, of course, one of the best things, again, still in the evening skies, we are in the winter, is the Orion Nebula, and that actually looks pretty good through binoculars, but better still through a telescope. That's just below Orion's belt. So the Orion Nebula is a good example of a region of young star formation. Orion is about 1,300 light years away, so that light we're seeing as it left when the Earth was in its medieval period. And most of the young nebulae where stars are forming are in the range of a few hundred light years up to about 1,000 light years away. Orion's an obvious one. The Taurus Nebula is another. If you have access to the southern sky, the Tarantula Nebula, and other regions that are closer to the plane of the Milky Way. And in fact, part of the reason we don't seem to have a lot of nebula to look at in the north is because we do not have a privileged view of the plane of our galaxy, the Milky Way, because most of the young stars in the galaxy are concentrated in the disk, the spiral disk of the Milky Way, which means we have to have a good view of the Milky Way. And the center of our galaxy, where the largest concentration of young stars and nebulae are, is in the Sagittarius constellation, which is pretty far in the southern sky from mid-latitudes in the north, but in the southern hemisphere rises almost passing overhead.
All right, the next question is from Tom, who's on with us live, who asks, I was wondering what is known about life on other planets, whether it is microscopic or not.
So other planets will start, of course, with the solar system. The supposition is that life, the most abundant life in the universe, is going to be microscopic or microbial, because life on Earth was microscopic for 2 billion years after life formed. The earliest evidence of life is about 3.7 to 3.8 billion years ago. Very recent evidence has pushed that closer to 4 billion years. But the first life forms that were large enough to see without a microscope took about 2 billion years after that to form. And then life didn't come onto the land until about 500 million years ago. So most life on Earth, for most of the history of the Earth, was microscopic or microbial, and we expect that to be the case elsewhere. In fact, it's not clear whether life ever need evolve to be large and have brains and be vertebrates the way humans are. Because evolution is quite happy developing microbial species, huge diversity of them on our planet, and it doesn't necessarily follow from evolution that you'll get anything larger. Within the solar system, the only plausible places for microbial life are subsurface regions of Mars, where we simply haven't been able to dig down deep enough to sample where those microbes might still exist, or possibly in some of the moons in the outer solar system, where we believe there is liquid water under a rocky and icy crust. That far from the sun, liquid water can exist because of the pressure of ice and rock, and some interior heating from the rock itself by radioactive decay. And if you take all of those, including, of course, Enceladus, a tiny moon of Saturn, where the heating actually comes from tidal flexing by the giant planet, then you're up to about a dozen potential places for microbial life in the solar system. But of course, they're extremely difficult places for us to explore in detail, and there are no life detection experiments planned in the near future. Even Mars is not going to get a true life detection experiment. When the twin of the Curiosity rover goes there, the so-called Mars 2020 mission, it will be an upgrade on the Curiosity set of instruments, but it's not actually going to contain true life detection experiments. And also Curiosity, the current one, nor its successor, will be able to dig deep into the Martian soil. So it's going to be tough to find microbial life in the solar system. As for microbial life beyond the solar system, we do know a few hundred Earth-like planets that are in situations where water could be liquid on their surface. And the main experiment we'll have to try and do, extremely difficult, and it's not yet been done, is to sniff the atmospheres of those Earth-like planets by spectroscopy and look for evidence of microbes by their metabolism. Obviously, the photosynthetic process on the Earth has generated a large flux of oxygen, the oxygen that we breathe. So early microbes on the Earth and subsequent organisms exchange carbon dioxide and oxygen through respiration. And that kind of signature, a non-equilibrium amount of oxygen in an atmosphere, would be a telltale sign of microbial life. So we're going to try and do that experiment probably in the next 5 to 8 years on a small set of Earth-like planets elsewhere.
Right, the next question is from one of our live viewers, and it seems many scientists have different theories of creation of the creation of our universe, how do we know that the Big Bang theory is the right one?
There are variations on the Big Bang, but actually most theories of cosmic origins involve something like a Big Bang, which is to say an early hot dense state 13.8 billion years ago. The reason why pretty much we've settled on that one theory or variations on that theory is a set of three pieces of evidence. The first is the expanding universe. That was first measured by Edwin Hubble starting in 1929, and then with a larger set of observations involving thousands of galaxies to show that they're all redshifted and that the amount of their recession velocity or redshift increases with distance. And that's the signature of a cosmic three-dimensional expansion, where we're not at the center, every galaxy sees the same thing. And if you trace that expansion backwards, you imply a time in the past, billions of years ago, when the universe was hotter and denser and all galaxies were on top of each other. The second piece of evidence is the amount of helium in the universe, which cannot be explained by the sum of all stars producing helium from hydrogen, as the sun is doing, over cosmic time. There's too much helium. However, the universe itself, in the first few minutes, was dense enough and hot enough to make helium in the same way that a star does, but in a non-equilibrium way because it was expanding, so it could only do so for a minute or so. But the calculations of the early universe and the Big Bang give you just the right amount of helium to match what we observe in the universe. So that's a very strong affirmation of the idea of a hot Big Bang. And then the third piece of evidence is, of course, the microwave background radiation, the uniform bath, almost uniform to 1 part in 10 to the 5 bath of microwave photons with a thermal temperature of 2.7 degrees Kelvin that we see in every direction of the sky. They essentially fill the universe. That's the radiation left over from the Big Bang, and its temperature is exactly what we would expect to be left over from the Big Bang. The radiation left, or was traveling to us since about 400,000 years after the Big Bang, when stable atoms formed. And so those photons no longer interacted in the voids of space and have traveled freely since then, cooling or redshifting by the expansion by a factor of 1,000. That also matches a Big Bang theory perfectly. And so these three pieces of evidence are why the Big Bang is the preeminent theory for the origin of the universe, and no theory has really come along to displace it. Any theory that competed with the Big Bang would have to explain the microwaves, would have to explain the amount of helium in the universe, and would have to explain the Hubble expansion. And that's quite a high bar to clear for some completely different theory of cosmic origins.
Right, the next question is from Bruna, who is online from Brazil, live with us. I would like to know if you watched the movie Interstellar, and what do you think about the way that they explored black holes and gravity?
Yeah, I saw Interstellar, and I was eager to see it, of course, because science, that kind of science, black holes and transporting through space and time with a wormhole, these ideas don't appear often in sort of high quality science fiction on TV or film. Interstellar benefited from Kip Thorne, one of the three main architects of the LIGO gravity wave experiment, who almost certainly will get a Nobel Prize, along with his two compatriots in that project for the discovery of gravity waves recently. So Kip Thorne was the scientific advisor on Interstellar, and he worked with Christopher Nolan, the director, quite closely. Now, Nolan didn't always accept Thorne's recommendations. I read articles, interviews with Thorne, where it was clear that occasionally there were creative differences, and in that case, it is the director's film, and so the scientific consultant tends to get overruled. But Thorne made it clear that it was a reasonable collaboration where most of the science was preserved. And in fact, Thorne and his group at Caltech ran a whole set of simulations, gravity simulations, to try and simulate in a supercomputer what it would look like to be so near a black hole. Gargantua is the name of the object in the film. And so that was done quite realistically, because it was actually based on supercomputer simulations run for that specific purpose. And so Thorne thinks the science in the movie is fairly accurate. There's some artistic license taken, which is reasonable enough, because you have to make a creative piece of work, a dramatic arc and a narrative and so on, and sometimes that doesn't accord with science. But I'd say on the scale of 1 to 10, where 10 is perfectly scientifically accurate and 0 is totally off base and off the wall for science, Interstellar probably ranks at somewhere like a 7 or an 8.
Right. The next question is from Robin, who asks, info from other astronomy classes and websites has said that some galaxies are moving at more than the speed of light. If that's the case, then what about E equals mc squared?
Right. So that information is correct. There are galaxies that, as we speak, are receding from us in the sense of a redshift, because the universe is expanding faster than the speed of light. So first of all, does that not violate relativity? Well, yes, it violates special theory of relativity, but Einstein's general theory of relativity has a different framework. Special relativity really applies to terrestrial scale experiments or lab experiments where you're shining beams of light or communicating or synchronizing clocks to try and keep time. And in those situations, those sort of small scale situations, the scale of a solar system and smaller, there is nothing can travel faster than light, and it is the absolute speed limit. The general theory of relativity was built to explain non-uniform motion, accelerated motion, and also to be built around the idea of gravity and curved space-time. And in general relativity, the expanding universe, where space-time can be curved, the expansion is governed by the theory of gravity and not by special relativity. So there's no speed limit attached to the expansion of the universe in the Big Bang theory. It's perfectly accounted for by general relativity, and general relativity accommodates superluminal expansion, faster than light expansion. And if you go through the history of the universe, it turns out the first third of the history of the universe, we're 13.8 billion years out, involved situations where every point in space was moving away from every other point in space at light speed or faster. And the further back you go, the more extreme that exceeding the speed limit of light was for space-time itself. So that's completely consistent with general relativity. What that means, however, you might wonder then, how therefore can we get information from places that have been receding from us faster than light? And the answer is dark matter. So in the universe, there's dark energy, which accelerates the expansion, especially in the last 5 billion years. But before that, there was dark matter dominant, which was decelerating the expansion. And so those regions that very early on were moving away from us faster than light have been slowed down by the action of dark matter in the universe to recede less than the speed of light. And at that point, the light signal can eventually reach us. And so it is possible to learn about objects which at the time their light was emitted were receding faster than the speed of light, if you can wait long enough. Now, playing that into the future, there's a problem because dark energy is accelerating the expansion. So those same objects that we originally couldn't have seen and that subsequently we have been able to see, they might once again become invisible as they're pulled faster than the speed of light away from us by dark energy.
Right, the next question from a live viewer is, how is the age of the universe determined and at what precision?
So the age of the universe is really measured, and the most accurate numbers you'll see anywhere are determined from a model, the Big Bang model. So accepting the cosmic expansion and the idea of a Big Bang, astronomers try and measure the parameters of the Big Bang model. And primarily that means measuring the amount of dark energy and dark matter in the universe. The amount of normal matter, the atoms of which our bodies, the Earth, the Sun, and all stars are made of, is about 4% of the universe. Dark matter is about 24%, and the rest is dark energy. So with those three components of the universe measured by different methods, you hope for more than one different method, then the expansion history of the universe is determined. And then you just trace back the expansion history with a model to predict the time when everything was on top of everything else, or the temperature, infinite temperature and density in the Big Bang. And in the model, that number is, I think, 13.772 billion years. And the precision is around about 1% in the model. It's quite an impressive number to know the age of the universe accurate to 1%, all that long ago. That 1% is a measurement error in terms of the data that goes into that calculation. But if the Big Bang model turns out to be wrong for any reason, then of course the age measurement, the precision of it is meaningless because it could be completely wrong. But there's no evidence that it is. Since we get the age from a model, a Big Bang model, it's reassuring if we can have an independent measurement of the age of the universe that doesn't depend on anything in cosmology. And the way astronomers do that is they try to measure the age of the oldest stellar objects in the universe. Those are typically halo stars in the Milky Way galaxy that formed the very earliest stages of the Milky Way, globular clusters, which are the oldest star groups in the Milky Way galaxy, or the age of older galaxies further away in space. Those methods are consistent with the Big Bang age. Obviously, they don't give the same age because these objects formed subsequent to the Big Bang, and they may have taken 500 million or 1 billion years to form. Like the earliest pieces of the Milky Way were probably about 1 billion years after the Big Bang. But they're consistent with the Big Bang age, and that's really important. A completely independent method is to use nucleocosmochronology, which involves the decay of radioactive isotopes in pristine or primordial solar system material. And that method is very interesting because it's based purely on nuclear physics. Unfortunately, the errors are rather large. However, reassuringly, those ages from nuclear physics and radioactive decay are also consistent with the Big Bang age. So astronomers are therefore pretty confident that they know the age of the universe.
Right. The next live question is, what about other dimensions? How is it possible to understand the reality of whether they exist?
The possibility of other dimensions arises these days from string theory, but even before string theory, the possibility of multiple dimensions was accommodated by the mathematics of general relativity, or just pure mathematics itself. It turns out that the geometry of multidimensional space was calculated 150 years ago by mathematicians, not physicists even, by mathematicians in Germany and Russia. Bolyai and Lobachevsky were two of the most prominent Russian theorists working on multidimensional space. In other words, if you take the sort of Euclidean 3 dimensions of space, x, y, and z, you can generalize the mathematical formalism that describes space or movements through space or geometry, volumes, areas, etc. You can generalize that into higher dimensions, as many as you like, in fact, because it's based only on mathematics, with no insistence that those higher dimensions correspond to physical reality. So the apparatus, the mathematical apparatus of multidimensional space existed long before general relativity. In general relativity, those higher dimensions are not present, but what we do is hybridize the 3 dimensions of space with 1 of time. These things are now united, and they actually have interplay with each other, and so that's where we come up with the idea of space-time. Then you move forward to the 1970s and 80s, where to solve some underlying problems with the standard model of particle physics and the idea of the fundamental nature of matter, theorists start reaching for theories that naturally, from their mathematical basis, involve higher dimensions of space. These are sometimes called M theory. It's string theory in the most general terms, but the theory that has the multiple dimensions most well developed is called M theory, M for membrane. And these theories tend to have 10 dimensions of space and 1 of time. And in a theory like that, the explanation given for the fact that those other dimensions, the extra ones, are not visible, is that they're only manifest on incredibly small scales and at incredibly high energies, the kind of energies that might apply in the very first instant of the Big Bang. So that's where string theory has gone in the exploration of other dimensions of space. So mathematics is pretty well developed, and the question becomes, do those extra dimensions, which in the theory are generally compactified, that's the technical term for the fact that they're all rolled up into a space far smaller than a proton or a subatomic particle, do those dimensions exist, and how would we know about them? At the first glance, it's not very promising to try and test these theories, because the energies required to realize these hidden dimensions are something like 18 or 19 orders of magnitude, factors of 10, beyond what any accelerator can do on the Earth. However, there are variations of these multidimensional theories where the extra dimensions possibly manifest on almost macroscopic scale, the millimeters or centimeters, where conceivably there are lab experiments that might test the presence of these hidden dimensions. And those experiments are underway in a number of physics labs. So as we speak, there is no evidence whatsoever of hidden dimensions or extra dimensions, but the theorists are confident that string theory, or M theory, is a good theory for the underlying nature of matter, and so they are confident that it's reasonable theorizing, and they're working hard to try and make testable predictions.
Right, our next question is, what is the likelihood of finding life on other exoplanets in the next decade?
I think it's about a coin toss, and if you're asking about the next decade, I'd say 50-50. And the reason is that we've learned a lot about Earth-like planets. There are several hundred. Most of these, because they're found by Kepler, are a few hundred light years away. So they're pretty faint, or rather the stars that these planets orbit are faint. And our handle on the planets themselves does depend at some level on the brightness of the star and their distance. So these are tough targets for any telescope. And James Webb Space Telescope is designed in part to be able to take infrared spectra of super-Earths or perhaps Earth-like planets and look for alteration of those atmospheres by biology. We also have large ground-based telescopes, such as the GMT that we're building here in Arizona. Rather, the mirrors are being constructed here. The telescope will go in Chile. And that telescope is expecting first light. James Webb Space Telescope will be launched in October 2018 and start delivering science data in 2019. Our GMT 22-meter telescope, which definitely has the light gathering power to detect Earth-like planet atmospheres and do spectroscopy, will get its first light probably 2020 and be at full strength at 2022. So those are both within the time frame of the next decade. And so I think by one or other of those type of telescope experiments, we have a good chance of finding life by this indirect method of spectroscopy of the atmosphere of an Earth-like planet.
All right, the next question is from Robert, who's on with us live, who asks, if gravity is a negative force and dark energy is a positive force, do they interact to zero out somehow?
It's an interesting question. They are opposite in some sense. Gravity universally attractive, dark energy universally repulsive. If you're talking about a physics type of version of this, it's the equation of state, which is negative equation of state for dark energy and positive for matter and mass energy. The possibility that they could balance out is plausible. And of course, there was a point in the history of the universe about 5 billion years ago when there was an inflection or change of slope, fundamental change of slope in the expansion rate of the universe, where the expansion rate of the universe turned from decreasing to increasing. That is, deceleration turned into acceleration. Now, that didn't actually imply a formal balance between dark energy and dark matter, because the universe was, of course, expanding throughout that. It wasn't that the universe was poised in a fixed state and could either collapse or expand, depending on which force was stronger. So the universe has always been in a situation where the gravitational potential energy, which is the gravity of everything acting on everything else, has always been negative because there's universal expansion. But that rate of expansion has changed. People think at the moment that dark energy is a completely different physical phenomenon from matter, whether dark matter or normal matter. So at the moment in physics, there's no obvious thing that would link these two major components of the universe. So in that sense, the answer to the question is no. But given the little we know about dark energy, I think a lot of physicists are hedging their bet. And some of them hope there is a deeper relationship between these two components of the universe that are actually very similar in strength. And there's no obvious reason a priori why that should be the case.
All right, the next question from someone who's on with us live is, what went wrong with ESA's Mars lander?
They've not given the full report. It tends to take months for these things to say what actually went wrong. But it seems like at the final phase of landing and deployment, to where you arrange a soft landing, there was a fundamental failure in a system component. And that's, of course, these are the highest hazard parts of any mission. The two most hazardous points in any planetary probe are the injection into an orbit, because having traveled at much higher than escape velocity from Mars through interplanetary space, there has to be a deceleration and a capture into an orbit, so you don't just spin off into deep space. There have been a few probes that have been lost by not getting that right. And the second obvious danger phase is deceleration and a soft landing, which relies on a very precise trajectory and extremely precise timing of the firing the retro rockets or whatever stabilization mechanism reduces to slow speed for a soft landing. And it seems like in that final phase, the Mars lander from the Europeans, had a failure, probably of a retro or a thruster, or perhaps even just a control system, and they haven't revealed which it was.
All right, the next question is, how long does a solar cycle last?
The full solar cycle is 22 years. The sunspot cycle is 11 years. That's the time between two consecutive sunspot minima or sunspot maxima. However, the sun is flipping its magnetic field, and so the full cycle corresponds to the sun's north and south poles swapping and then swapping back again to get to the original state. The cause of this is the winding up of the magnetic field. The sun, not being a solid object, it rotates differentially. So the equator is spinning faster than the high latitude regions or the poles. And since the sun as a plasma is threaded with magnetic field, that magnetic field spins up. So the dipole magnetic field, like a bar magnet of the sun, is going to gradually get wound up at the equator, by the equator moving faster. And at some point, that winding of the magnetic field leads the field lines to touch and reconnect, and the magnetic field essentially dissipates and has to reform from a seed magnetic field that's always present in the sun. And it tends to flip as it does that. And so the full cycle is 22 years. This, of course, was first seen after the invention of a telescope. Without sunspots, which are the sort of tracers, if you like, the canaries in the gold mine of the sunspot cycle, nobody could know what the solar cycle was.
All right, the next question is from Moses, who is on with us live. What about Kepler's discovery of an Earth 2.0? What is the degree of accuracy to which this assumption can be made? Or is this more like the Mars of the 1890s, when we assumed it could be habitable and discovered otherwise?
It's a good question, because there's been a little backlash in the science literature among astronomers over the slightly cavalier use of the word Earth-like, the term Earth-like. What does that actually mean? So let's just remember so it's a good question, because this is an issue that's coming up in the popular press, but also in the scientific literature, and people talk about it at meetings on exoplanets. So we should remember what mostly is measured for the vast majority of the Earth-like planets that are claimed is a size based on Kepler detection. The size is essentially the amount of the fraction, the area of the exoplanet relative to the area of the star that it orbits, which says what percentage dip in brightness when there's a transit. So Kepler measures a size. And the truth is that the most reliable Earth-like planet measurements rely on the Doppler method and the transit method both coming into play. Because transits give you size, Doppler method gives you mass. And mass and size give you density. And now you have that, so those two bits of information, those two different detection methods of the planet, give you much more certainty that you're talking about a rocky terrestrial object, which may or may not have oceans and atmosphere. Remember, the oceans and atmosphere of the Earth are a tiny fraction of its overall mass. So none of these detection methods in and of itself is going to be able to talk about whether there's water or an atmosphere on the planet. So if you're lucky, you have size and you have mass, and so you have mean density, and you can probably infer rocky material, a rocky planet, terrestrial planet, i.e. not a gas giant. And then based on the mass and the distance from its star, you can say what the surface temperature of this rocky planet should be. Also, based on its mass, you can say what kind of gases it's likely to have around it as an atmosphere, either gas that bubbled up from interior, outgassing, or gas that was captured in the initial nebula, or gas that was produced by the planet itself. Volcanic activity leads to carbon dioxide. Microbial activity, of course, can change the atmosphere too. So most of those things are far less well known. So that's the limit to Earth-like planet. Basically, we can never say yet whether these planets have true terrestrial geology, whether they have an atmosphere that's like the Earth, whether they have oceans that are similar in size or in fraction of the mass to the Earth. These are guesses, basically, at this point. And it's going to take probably a decade before even a handful of the Earth-like planets are characterized in terms of what their real atmospheres are and whether they have oceans on their surface.
All right, the next question is, how can the James Webb Telescope be tested on Earth?
It's tricky because James Webb deploys at a distance of 1 million kilometers, 1.5 million kilometers from the Earth. And so all you can do is test all the components. Now, the project learned a lot from the mistake of Hubble, where Hubble was launched with spherical aberration. And the reason that bad mistake with Hubble happened is because they didn't do a full-up test of the telescope assembly with everything in it. Well, having learned the lesson the hard way, James Webb has been fully tested, which is to say the optical telescope assembly, the OTA, to use NASA jargon, has been tested. And so all the mechanisms that will have to operate in the vacuum of space have been tested, which is to say the mechanisms that unfold the telescope, because it is fitting into a much smaller space to be launched than the eventual size of the telescope. So the petals have to unfold. The telescope also has to unfold a solar panel or solar array about the size of a tennis court that's folded like an accordion into a much smaller space, and that also has been tested on the Earth. So all these things have been tested. The trouble is it's not and can't be exactly the conditions that will apply when it really deploys, because those will be conditions of deep space, of vacuum, of high cosmic ray and ultraviolet energy deposition, and possibly some stress from radiation and solar radiation. So it's tested as well as it can be, but there's certainly high anxiety amongst the engineers in that project over the number of moving parts that have to work well for James Webb to be a successful telescope. And at a position where if anything's wrong or anything fundamentally doesn't work, there's no way to fix it.
Right, the next question is Planet 9 real?
So at the moment, there's no evidence for a so-called Planet 9. Planet 9, that's actually been used for two different concepts. I mean, one is a sort of, large planet, Pluto or larger, out in the Kuiper Belt or beyond the orbit of Pluto. And those searches are underway, and some other dwarf planets have been found, and a few more may still be found. Another historical use for Planet 9 was the idea of a large planet in an interior orbit, sort of counter orbiting where the Earth is, so that to always appear behind the sun, which is a convenient way for us not to be able to see it very easily. There's certainly no evidence for a large interior planet, and that's not because something couldn't possibly be hiding behind the sun in the opposite part of the orbit of the Earth. It's just because gravitational calculations don't allow any large object to be missing in the inner solar system. But as far as large planets, certainly bigger than Pluto, possibly Neptune or Uranus size, further out than 40 astronomical units, so out to 80, maybe 100 astronomical units, the Kuiper Belt, it's absolutely possible that such a planet exists. And because of the interactions of planets with other rocky debris, those planets might plausibly have large inclinations relative to the plane of the solar system, which means when you search for them, you actually have to search quite a wide strip of sky beyond the ecliptic itself. And that makes finding such a very distant, very faint, and slowly moving object really difficult. It's going to take the surveys that are underway 3 or 4 more years to be sure there's no large Planet 9 out there.
All right, the next question is, can satellites help predict ocean level rise?
So satellites are playing a really important role in monitoring the health of the planet. Most people don't realize, but NASA does a lot of Earth science. NASA's budget is roughly $18.5 billion a year, and that's divided into, propulsion technology, International Space Station, developing successor to the space shuttle, space science like telescopes and James Webb and Hubble, planetary science, all the various probes. And there's Earth science. And actually, Earth science gets a bite of NASA's budget that's somewhere between $1 and $2 billion a year. I don't remember the exact number. And a lot of that is done by downward-looking satellites. So we're used to NASA sort of looking outward into space and the rest of the universe. But a lot of the probes that NASA launches are part of arrays of Earth sensing, remote sensing satellites to look, and they look at various things. And they're definitely looking at ocean rise or sea rise changes. They're also looking, doing reflectance work to try and look at deforestation and see the changing vegetation patterns of the Earth, because that has an implication for climate change. They're also trying to diagnose fish stocks. They're diagnosing forest fires or other things that will alter the terrestrial environment by putting contaminants in the air. So this monitoring work of NASA satellites, dozens of them actually at any given time, is really important Earth science. It's also important in this whole game of realizing how the different aspects of the terrestrial ecosystem interact with each other. So we already know that the biosphere, the living part of the Earth, interacts strongly with the atmosphere. It interacts with the oceans, and it interacts with geology, with the terrestrial surface itself. And these kind of NASA experiments are telling us a lot about those detailed relationships and interactions.
All right, the next question is, what is the main reason carbon became the basis for life? Could oxygen or nitrogen have been as well?
Carbon is available. It's one of the most abundant elements in the universe. So in terms of cosmic abundance, the dominant abundance is hydrogen, then next is helium, and then the biogenic elements, carbon, nitrogen, and oxygen, are roughly similar abundance, a few hundred times less abundant than helium and hydrogen. And that's a cosmic average. So we expect nitrogen, carbon, and oxygen to be available in most rocky environments anywhere in the universe. So why then is the carbon the basis for biology on the Earth and maybe elsewhere? It's because of the nature of carbon's chemistry. Carbon has the ability to form 3 covalent bonds, and so it is very prolific in terms of forming relationships with other atoms. In particular, it easily can form bonds with multiple other carbon atoms, and from that basis, it can go on to make chains and loops and spirals and all sorts of 3-dimensional patterns. So carbon and then other atoms, nitrogen, oxygen, phosphorus, sulfur, other atoms that are available in abundant forms, can then build complex molecules. So carbon is unique because of its valence chemistry in forming long chains or very long complex molecules. In fact, the limit on the size of organic molecules is unbounded. The Handbook of Physics and Chemistry, is over 1,500, I think, maybe almost 2,000 pages long, and it's listing very long organic molecules through most of it, which are just increasing numbers of carbon atoms with hydrogens hanging off them, and so on. And you can just keep building these essentially forever. So no other element in the periodic table has this ability. Because it lies in the same column in the periodic table, in terms of its electron and valence structure, silicon is another potential candidate, but the people who do lab work on silicon find that it does not form as robust bonds as carbon. It's not as stable, and it doesn't form the same sort of prolific mix of different molecules. So while silicon biochemistry is possible theoretically, given the abundance of carbon, its availability, and the fact that it's brilliant at making complex molecules, it's almost certain that biology anywhere in the universe will be based on carbon.
Right, a couple people have the thought as to whether it is possible to see the gravitational lensing effect using a large amateur, like a Dobsonian telescope.
Basically, no, because if I think about it, the brightest examples of gravitational lensing are really faint, and I'll put some numbers on that. The gravitational lensing that you can see, where the image splitting, where the separation of the images or distortion of images is visible beyond the seeing of the Earth as 1 or 2 arc seconds, that limits you to a small number of objects. So the classic archetypal lens quasar, the 0957 plus 056 plus 056, I think is the full designation. That's the double quasar. And that is, if you had a 20-inch telescope, you would be able to see that double image quasar. It has a 6 arc second separation. So that's one. So the prototype lens quasar is visible through a significant sized amateur telescope on a dark site. But to go beyond that and see many other lens quasars gets really hard, because the next brightest examples are 2 to 4 times fainter, and their image separations start to get down to 1 or 2 arc seconds. So you need really good seeing and even more light gathering power. The other forms of lensing are, of course, galaxy arcs. And the problem with those are really beyond the realm of modest or even medium-sized amateur telescopes. And the problem there is not that the arcs aren't spread over a large distance of sky. When there's a lensing arcs in a cluster, they can be spread over an area the size of the full moon. But the surface brightness, or the number of light photons relative to the darkness of the sky, is very low. And typically 1 or 2 meter telescopes at the minimum are needed to see gravitational lensed arcs of galaxies. So the answer is not absolutely no. You probably have a small handful of lens quasars you could see, but all of the galaxy arcs are pretty much beyond any amateur capability.
All right, the next question is, does time really stop inside a black hole?
So inside a black hole, we don't know, and probably not. What we can say in terms of relativity and the understanding of black holes is that if you did the thought experiment of tossing a clock, or not a mechanical clock, let's say an atomic clock or a high precision clock with a readout, into a black hole from a distance, and then you had, say, an identical clock keeping time well away from the black hole, and you're just watching what happens. If you did that experiment, then the clock that fell into the black hole would, if you were with that clock, so you went in holding that clock, would just seem to keep normal time. From your perception to time, the rate of time passing on that atomic clock wouldn't change. At some point, as you accelerate towards the black hole, you'd pass through the event horizon, lose all communication with the outside world, obviously at some point be crushed to death at the singularity or inside the black hole, but the time would flow seemingly normally. The bizarre aspect of relativity in black holes is that to the outside observer, who has the second clock, identical clock, their clock would, of course, keep normal time, but as they watch the clock falling in, that clock would appear to go slower and slower as it approached the event horizon. And in the theory of black holes, the clock falling in never actually reaches the event horizon. It asymptotically takes an infinite amount of time to reach the event horizon, while time slows at an asymptotically slower rate, eventually freezing completely. Simultaneously with this, there's gravitational redshift, so the radiation, the light that even let you see this clock falling in, would be redshifted to extremely low and eventually infinitely low energies. So time freezes asymptotically at the event horizon, as seen by a distant observer. But to the observer with the clock, they just fall in through the event horizon to an unknown fate. It's a bizarre aspect of black holes that, of course, we haven't been able to test.
All right, this is probably going to be our last question. But we had a couple of people, different people ask about this. And the question is, since we've talked about time being relative, and our time is different than some other place in the universe that's traveling at a different velocity, how is it that we can say that the universe is 13.8 billion years old? Is that, locally, or would it appear different to other people in other galaxies far away from us moving at different speeds?
Right. So that's a good question. When we talk about age of the universe or cosmic time, we do it from our perspective. So how can we be so sure that that's meaningful across the universe? And the simple answer is we can't be sure. The premise of cosmology is based on what's called the cosmological principle, which is the idea that our location in space is not special. And so if we were situated on another galaxy millions or billions of light years away, we would also see a Hubble expansion. We'd see an expanding universe, an accelerating expanding universe because of dark energy. That's a presumption of cosmology, and we've seen nothing to counter that. But it still is an assumption, and it's an assumption because we simply can't displace our perspective, our point of view, very far at all. The best we can do is move with the Earth in its orbit of the Sun and very, very slowly travel around the galaxy on a big looping circular orbit, but we can't change our perspective on the universe at large. And so we can't do the experiment of seeing whether truly we'd measure the same expansion rate and age of the universe if we were on another galaxy. However, nothing in our observations of the universe has shown that we have any privileged position. So we imagine that the cosmic expansion is occurring in 3 dimensions, and that an observer on any other galaxy would see the same expansion on average. And if they projected the expansion backwards with a Big Bang model, they calculate the same age of the universe. So we have a moderate degree of confidence that when we measure the age of the universe, it's not just our answer, it would be everyone's answer. But it's important to realize that is based on an assumption about how the universe works, a simplifying assumption that we call the cosmological principle. So I think that's all for today, and thanks for, as always, your very good questions, and we'll be back with you in a couple of weeks. We'll get one more in, of course, in December before the holidays. Thank you.